Right, let's see where this takes us. From this relationship, we can write that P times V is equal to a constant. Now that would be P is equal to a constant over V, so PV is equal to some constant. Here we can write that P over T is equal to a constant. And here we can write that V over, now remember, I think what we should do is say NT because we're
saying the number of
is equal to a constant. Now, the mathematicians are not going to love me for this, but let's fudge this. We've got all of these things as a constant. And what I'm going to say is that if we put all of these together, what we get is PV over NT is equal to some constant.
Yes.
Okay, as I say, no mathematician is going to love me for doing that in such a cavalier fashion, but this is in fact the way it turns out, is that the pressure, the volume, divided by the number of moles times the temperature in Kelvin is equal to a constant. And this constant is a constant which is called R, and it is called the universal
gas constant.
We can see the units of pressure are going to be newtons per square meter. Volume will be meters cubed, so P times V will be Newton meters, divided by, well, the number of moles and Kelvin, and this in fact has a value of 8,314 or 8,315 depending on which textbook you look at, and the units, Newton meters, is joules per Kelvin per mole. And that is the universal gas constant. Now, the beauty of this number is that if I take the pressure and the volume for a fixed mass of gas at a certain temperature and I calculate that value, it will come out to something either exactly equal to or very close to that. An ideal gas will remain at that value. When we deviate from the ideal behavior, we get a figure slightly different from that. But for ideal gases, that is the value that we can take. Now, that means that we've got a relationship here. PV is equal to N times R times T. And just look at it very quickly. If I keep volume constant, N is constant and R is constant. Keeping volume constant, P is proportional to T. If I keep pressure constant, N is constant, R is constant, V is proportional to T. And if I vary, if I keep temperature constant, then nRT is constant, so PV is equal to a constant, so P is equal to a constant times 1 over V. In other words, there's an inverse relationship. And all of this depends on using the correct temperature scale. In other words, the temperature scale which goes to 0 when the pressure drops to 0.
Yes, and that's the Kelvin scale.
Well, that is quite a mouthful, and you will find this treated very adequately in every textbook. What we'd like to finish off with is just one quick look at a graph relating two of these variables where things deviate slightly from ideal behavior.
Now, this is a graph that gives us a relationship between volume and temperature for a fixed amount of gas. Now, you would see here that the red line here, it's a straight line, and it represents the behavior of an ideal gas. In other words, that non-existent gas that we explained earlier on. But the dotted line represents our real gases, say nitrogen or oxygen. Now, let's carefully look at what happens towards the bottom of this graph where we're looking at the points next to 0. What we see happening is that the ideal gas actually starts from a point where if the temperature is 0, we can expect the volume of those molecules of the gas to be occupying a 0 volume. Now remember what we said about ideal gases, that they occupy no volume. So that is actually explained by that part of the graph there. But look carefully at what is happening with the ideal gas curve, the dotted curve there.
The real gas curve.
The real gas curve there. Yeah, we've got a space between 0 and some value along the v-axis there. So that tells us that actually the real gases occupy volume, and that also tells us that at low temperatures, very low temperatures, and also very high pressures, the real gas will always deviate in behavior from the behavior of an ideal gas.
Because real gases have real
volumes.
Okay, we can't imagine they're just plain points.
No ways.
Okay. There are quite a few of these graphs that one can look at and then try and look, as we said, look at the ideal curve and say, okay, that's when everything's perfect. It has no volume, there are no cohesive forces, etc., etc. And then look at the real gas curve, and of course different kinds of real gases have different types of deviation. And we can say, okay, look what's happening here. There are cohesive forces, there is a volume, etc.
Exactly. Very interesting curves, and I think it's worth looking at them. Go check your books as well to have more on this. Thank you so much for watching. This is all we had for you today. Tinyika Wamachavkosa. Bye-bye.
And Peter Glover saying farewell.
Summary. In this lesson, you learned about physical processes and phase changes, the kinetic theory of matter, ideal gases.